the team behind it all. Okay, I suppose I'll give you guys a quick tour of the lab and or our experimental setup. So I suppose the first and one of the more boring things we have to show is our combustion chamber. And so this is a glass chamber we had built in the last 6 months. And more or less, we just have the general mixing chamber. And then towards the side, we hope that these holes will promote an even distribution of our aerosol. And then we have our 2 sampling ports at the top. We do our burns of our leaves. They're just a bit hard to see from this shot. But we have a hole in the bottom of the chamber that we can put a lighter through to light our leaves on fire without having to actually open the glass windows of the chamber itself. So on the top of the chamber, we have our Ducati diluter. This diluter is just to reduce the overall concentration of the aerosol that is making its way to some of our more sensitive instruments. And then we have our, I suppose, our sensitive instrument, which is our AMS. And so that's it. Johanna will go through some more detail about the AMS itself shortly. And then we have our old SMPS towards the back here. It's not the most exciting bit. We have our dust track. So we have the computers. And then this mess at the back here is the pink, or the particle internitroxide quencher. Okay, I suppose while I've got the camera and microphone, I'll run through talking about the pink first for you guys. So the pink, I don't know how much Zoran has told you guys about it, but the pink, it collects aerosols into our liquid solutions pretty much as the first step. So it does this by first, it grows the aerosol into a larger size. And this is done by our steam generator here. This is our, the outer sheath is Teflon. Ooh, I just went slip. Okay, the outer sheath is Teflon, the inside is an aluminium block. And you can see down here is my control box for the pink. It's currently set to 145 degrees, and it's constantly measured with a thermocouple. And so the idea of this steam generator is there is constantly a 1.5 mil per minute flow of liquid into the steam generator, and then it produces a steady stream of steam through the output purely by the buildup of pressure from the water going from liquid phase to gas phase. It generates pressure, and then it will shoot maybe a meter long jet of steam if it is not hooked up to the pink. Unfortunately, for time constraints, I won't try and show you guys that. The next step of the pink we have is we have our growth chamber. There's not really much to see along the growth chamber itself. It's purely just the connections. And then so within here, this piece is actually where our growth happens. And then towards the end, there is another cone which focuses our aerosol. Something else to note is that the growth chamber is constantly cooled. This is to obviously try and avoid any variability between temperature during sampling, because the pink is designed to be a continuous instrument left on for 24 hours a day. So it's cooled because over time heat may build up in the system. So we'll move on to the more interesting, exciting bits. I'll try and get a shot of our liquid vortex at the back of the pink.
That's the one that for sample.
What was that, Zoran?
I was just saying that I've explained that part. Do you have it running? I think I can see the water swimming. Can you see the cone of water?
Yeah. Not particularly. You can't really see the vortex.
You can see a bit of water at the bottom.
Can you? Oh, yeah. Wait, I'll shine my phone torch on it. 1 sec. That might work better. If I do that. Nope, that's way too bright. I suppose you guys will just have to trust me that there's a spinning vortex of liquid there. Yeah, you can just see it. So anyway, so the pink has a very high collection efficiency for smaller size fractions of aerosol. And this is owed to the combination of the vortex collector itself and the growth chamber. So vortex collectors are great, but they're only good for collecting very large size aerosols. And so because of that drawback, we decided, well, I think it was Zoran's original idea, was to couple a vortex collector with a growth system. So our very small nanometer size aerosols will be grown in our growth chamber, and they will be of a size that the vortex collector can trap into the liquid with a very high efficiency. And so that is pretty much the main job of the entire body. So I suppose the next thing I'll just talk about is how we actually measure our ROS. So for measuring our ROS, we have our fluorescent probe. And so you can see my supply bottle here of my fluorescent liquid. So this is the unused liquid. It does start a bit fluorescent, but once upon exposure to ROS, it will become far more fluorescent far more quickly. And yeah, so we measure this change in fluorescence constantly from the back of the cyclone here. You can see I have my liquid tube, which is going through our custom-built flow-through cell fluorometer.
That's the small
And
one.
yeah, so this... What was that, Zoran?
Just show where the probe goes in and where it goes out.
Sure.
No, into the vortex.
Into the vortex.
See, that yellow liquid is the
Right.
aerosol solution. Probe goes up.
This is the liquid line in, and at the bottom here is my liquid line out.
Whirls around, captures the particle, and goes out. Okay.
What was that, sorry?
Nothing. Just supporting you.
Okay. All right. Where was I? Anyway, to control all our liquid flows into the system, so obviously we have our water supply for our steam generator. For this, we use milliQ water, purely because over time you can have some scale build up on the aluminium inside of the steam generator. And then I have 2 waste bottles and my nitroxide supply. So I suppose the only other thing of the pink that I haven't really covered is my lovely stainless steel flow switching assembly that I have here. So, you know, when we're measuring ROS, we can measure the total phase ROS and then the gas phase ROS, and then we calculate our particle phase ROS by subtracting the gas phase signal from the total phase signal. And yeah, so this is done by larger than it needs to be system, but simply we have our which has a 2.5 micrometer impactor. Is that it? Yeah. And then so our sampling line will come in. So if we're measuring total phase, obviously the flow, this valve will be closed, and so the flow will just go straight through. And then if we wanted to measure just gas phase, this valve will open and this will close, and then the flow will be going through a HEPA filter. Majority of the aerosol will be removed, and then it will go on to be sampled by the pink. I think that's it. Zoran, is there anything else you'd like me to say?
I'll ask, is there any questions? No? Okay, that's good. Thanks, Zach.
Thank you. I'll put Johanna on.
Johanna is our postdoc. She was a PhD student, and now she is a postdoc, and her PhD was on interaction between biogenic and anthropogenic sources. So understanding how biogenic compounds such as alpha-pinene and isoprene are oxidized in real atmosphere. So she was supposed to do those experiments both in Brisbane and China in one shot, but the China part was delayed because of COVID. Hannah, go ahead.
Okay, can you hear me?
Yep.
Perfect. So I'll quickly show you the SMPS for those. I don't know if Zoran have you told something about the SMPS?
No.
No. Okay. So hang on. Our aerosol. Oh, thanks. Comes in here through this line and passes through an aerosol neutralizer. So to charge the particles or neutralize to give a neutralized charge onto the particles. And then they come into this column here, which is our electrostatic classifier. And in this electrostatic classifier, so we apply voltages. At the moment, I'm having into scanning mode, which you can see here on the computer screen. So it scans through different particle sizes by applying a voltage to a rod, which is placed in the middle of this electrostatic classifier. And dependent on the electrical mobility of these particles, they enter at the bottom of the classifier. I don't know if you can see it. There is a small outlet here for the aerosols, so particles which have a specific size enter on the bottom here and get collected or counted by CPC. That's pretty much it, how the SMPS works. Now to the AMS. It's a little bit more complicated. So for the AMS, we have here an inlet. This inlet has a critical orifice of 100 microns. And the particles pass through, this is our inlet valve, into an aerodynamic lens system. I think Zoran told you a little bit about how the aerodynamic lens system works. So it basically focuses the particles. You have several plates of different diameter size. And so the particles here in the AMS, mostly between 100 nanometers and 550 nanometers, can pass this aerodynamic lens system up to 100%. And particles smaller and larger pass only to a specific percentage, and above or below 40 nanometers and above 2000 nanometers, the AMS is can't detect anything because of this aerodynamic lens system. After the aerodynamic lens, we have...
for a sec, Johanna. Yeah,
yes?
just stay there. So see that box? That's the lens. And below, we have a turbomolecular pump. So that's what I said. It has this differential sucking. So it takes most of the air out, the bottom pump.
Yeah.
And after that, the particles are in a stream. Yeah, continue.
So yeah, after this, after the pump, you have a skimmer. And so the skimmer, so this pump pumps out most of the air molecules. And after the skimmer, because of the shape of the skimmer, it has a conical shape. And we have here another vacuum pump, which sucks. So the vacuum here is 10 to the power of -3 in this whole system part here. So the particles, I don't know if you can see it if I zoom or show this here. Maybe not. It's reflecting too much. So yeah. No, I can't show you this one. So there is a spinning wheel in here. This is the chopper. So the particles pass this spinning wheel and it moves positions. It can move into open, blocked, and a chopped position. So in the blocked position, only the air molecules can pass through to give a baseline measurement. In the open position, all particles and the air molecules pass through. And in the chopped position, there are two slits on this spinning wheel, which are 180 degrees apart from each other. So really tiny slits. And the particles beam gets chopped. So only specific particle sizes or particles pass through. And dependent also after the skimmer, because of the lower pressure here and the shape of the skimmer, particles accelerate into the, or get accelerated in this particle chamber. And so larger particles or smaller particles fly faster than larger particles. So you can, dependent on the particle diameter, you can basically get the chemical composition, because large particles fly, or like you can, hang on. So dependent on the speed, pretty much they pass this chamber part faster or longer. And here on the back, hang on, maybe I can show it. Can you see this?
Yep.
So there is, in the middle of this, I don't know if you can see a black small hole in the middle. This is the heater. So the heater, these particles like get flash vaporized on this heater. So the heater is heated up to 600 degrees at the moment. And what you see glowing there is a filament. So there's a filament sitting pretty much under the heater. So
it's the electron source.
Yes, so you have the heater pretty much in the middle here of the chamber, and under it here there sits a filament, and you apply a voltage to up here. So basically the electrons which get emitted from this filament pass through the now aerosolized or vaporized particles and ionize these ones. So you get positive ions. And these positive ions fly into the TOF chamber, which is the chamber up here. So it's the time of flight chamber. And we have a lot of...
So the ions go like this.
Yes, so we have a lot of, as you can see here, cables which all apply voltages to specific parts of the time of flight chamber. So the particles enter here, they experience a pulse. So they get pulsed into this flight chamber, and they form like a V-shaped flight path. So we have a reflectron, it's called reflectron, which has at the back, it's just different plates which have specific voltages. So the particles get accelerated in here, decelerate in this reflectron, and get accelerated because here's another plate which has another voltage. So basically they make a V-shaped path, and then get detected here on the top. Okay, that's pretty much the AMS. So, and because you have the time, you know the flight paths and the flight lengths, so you can calculate your diameter and get then a size dissolved composition of your particles. Any questions?
Okay. Can I explain actually how the whole thing looks like? So it's roughly this size. If they make models where they remove that time of flight first part, the instrument which can only give you the composition, not the size dependent composition, the ACSM, aerosol chemical speciation monitor, to just downsize instruments like this, and they're really commonly used. They're much cheaper, more compact, and they're excellent for long-term, like monitoring. Leave it there and go for a year without touching, and it give you continuously particle composition versus time. And then almost half price of the full mass spectrometer. We are looking at buying a new one. This one is starting to fall apart in more than 15 years. And the new one will have a higher resolution time of flight mass spectrometer. So this is a compact, a small. We are applying for a higher resolution one that is twice the size. So there's a longer path. You can have higher mass resolution, so we can in more detail look into specific components. You have anything running or not?
Yes, we have everything pretty much running. So it's just connected to the chamber background. Hang on. So I can just show this screen, or maybe I can share the screen.
Share the screen.
If I find it there. This one. Can you see it?
Yes, we can.
Okay. Yeah, so this is just at the moment sampling pretty much what's in the chamber background. So we have, we can select between different species. So at the moment I have here the total organics selected, which is the green curve, the sulfates, which are in red, and here at the bottom I have the nitrates in blue, and ammonium in yellow, orange color. So at the moment, it's just sampling the background. So there's, you can see here for the species, the different ones. Can you see my cursor? Oh, yeah. So you have here the organics with mass to charge or smaller than 60 and higher than 60. You have nitrates, sulfates, ammonium chloride as well, and the water. And this is the total concentration you get at the moment in micrograms per cubic meter from all the aerosol. Yeah, so I can also show you, this is like how the actual mass spectrum looks like. So you have here your mass to charge ratio, and you can see the concentrations in micrograms per cubic meter for the different mass to charges. As well, again here, always organics are in green, sulfates in red, the ammonium is in yellow here, and nitrate peaks you have in blue.
Do you intend to burn anything in the chamber?
Yes, we plan to burn something.
So go ahead.
Okay. Okay, I'll hold that. It's still turned it so. Yeah, it is, but this one turned black.
Go a bit towards the left. Or
Better?
Yep. Can you stop sharing your screen, computer screen?
Yes.
Hi.
Sure, hang on. If I know where, it doesn't let me.
Okay, that's good. You stop sharing.
Okay. Did I stop sharing?
Yes, you did.
Okay. All right, I go back.
You're burning fairly small quantities in this chamber.
Just have to look. Did you burn everything? Oh. Yes, we have a lot, and we have too much for the AMS.
Okay, so show the screen for the AMS.
I just stopped. I closed the inlet because it was more than 400 micrograms per cubic meter.
We'll do the pink first, Zoran. How about that?
Okay.
Yes. I'll hand you back this one.
Please. Quickly.
Yeah. Alrighty. Oop.
U suštini ideš, mislim sad da je sve u Beogradu, samo ovako može se prikaže, ako ne odeš uži.
Da.
Da. Dobro, super. Slušaju.
Alrighty, go. So I've shared my screen, so you should be able to see the data output for the pink at the moment. Let me just adjust the scale here. Okay, there we go. You hear myself?
Can you turn off your mics, guys?
Hold up, Zoran. I need to turn my volume off.
Okay.
All right. Unfortunately, I mistakenly cleared the raw buffer, but it'll be fine. We should see signal shortly. So when we do our burns, we generally have a very sharp initial increase, which you could see before, but I also had a bunch of background data clogging the screen. But hopefully in the next minute, we should see our valve switch, and then we'll go from sampling gas phase to total phase, and we should see a sudden increase. When the pink is running, there's always a small amount of noise that you're going to get in your signal. And this is mostly purely from the occasional air bubble passing through the spectrometer. Yeah. Occasional, depending on the day, I should say. All right, so my valves have switched. So you can see now that I have a gray area, so that's indicating a different valve state. So hopefully we should see some difference. I knew I should have checked this setup. But unfortunately, we don't.
Your scale is stretched, that's why you can't. There's a small increase there.
Yeah, potentially. No. That scale is difficult to change. Is AMS happy yet? Who said that was enough dilution?
You see the increase down.
Yeah. I'm curious. It's chosen a good time to misbehave. Well, this is why we prepared a data set earlier, I suppose.
Yeah.
What else do we have to discuss?
Can we switch to the AMS? Meantime?
Unfortunately, no. I can show you. Hang on with the camera, just the screen. Can you see the scale?
Yep.
On this one. So as you can see, the it is increased up to 1,500 for a short time, which is way too high for the AMS. So I closed the inlet valve now. And I'm hoping that the concentration decreases at some time. Because at the moment we have from the dust track, as you can see, it's around 2 milligrams per cubic meter.
That's too much.
That's too much. Yeah, and the SMPS is also, it's really high, but you can at least see something from the SMPS. So you see a nice scan here. Particle sizes, so the mode roughly is at around 100 nanometers. Yeah. We can wait for the scan to finish. Yeah, I hope I can show you later. Once the concentration decreases a bit, I can show you the AMS, hopefully.
But when you see how quickly the instrument reacts, it's a matter of seconds, you can see the change in the composition.
From the AMS, yes.
Yeah.
Like, I can zoom in.
I can stop sharing.
So, you can see when we first connected or first had the burn, it was like roughly 300 micrograms per cubic meter in the AMS, and then I turned off the inlet, and then I tried it again, and it was like 1,500, so I turned it off straight again. But yeah, you can definitely see the change in the AMS from the chamber.
Okay, and you can see the peak that those spikes are bubbles, so it seems that we've got a lot of air in the system. Usually not that dirty, but then there's the whole post-processing where you actually have to remove the bubbles.
That's what I'm supposed to say.
Oh, you can see it now clearly going up.
We're looking at noise right now.
If it goes down to 1, I can probably turn it off.
How many counts is the CPC reading?
Oh, it's okay. The CPC is where the SMPS
So that's
is
7,000. So it's reading 7,000 counts diluted, right?
Yes.
The pink should see
So
a
what you
signal.
get is the cleaning today.
I don't think the pink is getting
This
any
guy
error.
looks dirty. in a way with all the
Yeah,
noise.
I just don't understand why the pink isn't seeing anything.
Yeah, the pink is going up. Yeah. You can see the switching particle phase, gas phase, just gas phase, now particle phase. And that delay that's needed for the signal to stabilize. And it's very noisy.
Yeah, I'm not too
Okay.
sure what's happening actually, Zoran. I believe the pink is actually not managing to get any aerosol coming through,
Ah,
which is interesting. Well,
Okay.
the pink hooked up to sample directly from the chamber,
Ah,
but maybe purely from the length, there's too many losses.
ah,
No.
too
Mm.
much.
This is-
Okay.
Yeah.
That's good. Thanks for the demonstration, guys.
Yeah.
That's all right.
Any questions here? You just I think it's good that you had an idea to see how the instruments look like, how they behave or misbehave. Because most of them are lab-based instruments, so
The misbehaving is the important part, all right?
yes, very common. That's why you have to repeat the experiment. Okay, thanks all guys for the demonstration, and thanks for the data as well.
It's all right.
No problem.
Okay,
Enjoy school.
yeah, we'll do. Be in touch.
Bye.
Bye.
Bye.